Yeah, let's continue on this start. I think this will be the last section in chapter 10. After that, we're going to study sequences and series and convergence, divergence. Okay. Now, in this section, we just use the polar coordinates to describe the curves in the xy plane, and then we get the special parametric equations. Then we use that to evaluate the length of the curve and there's a surface area of surface area of the surface generated by rotating the curve along some axis. Okay. So anyway, so we get the parametric equations using the polar equations. First of all, a curve, the polar equation usually, okay, is given by this. Okay, this is in polar coordinates. We call it the polar equation. Okay, then use a polar equation. I get parametric equations. So more details will be like that. So each of them depends on theta parametric. Okay, so that both describe the same curve, but this parametric equations in the in the Cartesian equations. Okay, parametric equation always it's in x y plane. Okay. We know that if you have a curve, right, how to find the length, right? This is arbitrary point x and y in the xy plane, right? The ds is going to be the original form is this, right? You can take theta out, so dx d theta squared, dy d theta squared d theta, okay? Then you differentiate the x and y given by the parametric equations. And in my last class, I did the computation. I find out this is just the dr d theta squared plus r squared d theta. Okay, it's great. So we can use that to find the length of the curve. Okay. So we can use as the length of a curve is going to be integral if the theta is between a and the b, and then you just have you just evaluate this integral. Okay, so we can talk about the area formula, integral for the area of the surface later. Okay, but the idea is similar. As long as we get the parametric equations, you can solve the problem. Okay, all right. So let's take a look at example. Find the exact length of the polar curve. When we say polar curve, it is described by the polar equation. Okay, I is going to be 5 to the theta. Theta is between 0 and 2 pi. Now, how does the graph look like? Clearly, when theta increases, the radius, the r increases, right? So I don't need to make a table, just sketch a graph, right? When theta equals 0, I is going to be 1, okay? But when you just rotate, right? You rotate this line counterclockwise, but when theta increases, I is getting larger, right? So you just, getting larger. Eventually you get I equals 5. 5 to the 2 pi actually, when theta equals 2 pi. Okay, when is a 5 to the 0? So this is a curve, right? We just need a sketch graph. You know, you don't need to get the precise picture. So using that, how to find the length, right? By the this curve, if we want to use parametric equations, the parametric equations will be x equals r, so 5 to the theta cosine theta, y equals 5 to the theta sine theta. Okay, this is a theta is between 0 and 2 pi. That's the parametric equations for the curve. Okay, but we can use that if we remember the above formula. You don't need to go through this step. So the length is going to be integral from 0 to 2 pi, and the derivative r with respect to theta square. Okay, that's it. And it will be surprised. We can easily find the length. Okay. So the derivative of r with respect to theta. This is an exponential function. So you will get 5 to the theta natural log of 5, right? And this is just 5 to the theta squared, the theta. Well, we can get rid of the radical. Why? Because they have the common factor 5 to the theta squared. Then natural log of 5 squared plus 1. That is constant, right? So you can take the constant out. Although there is still radical, but this is a constant. So you don't need to worry about it. So let's take the constant out. Okay. Now what is the antiderivative 5 to the theta? 5 to the theta, the antiderivative is 5 to the theta, natural log of 5. Then evaluate that's 2 endpoints. Okay. So we get, right? You get, just take the difference. 5 to the 2 pi minus 5 to the 0, which is 1. So that's what we get. All right, so our next problem, the polar equation is given by 1 plus cosine theta. We did a similar problem in the last class. Okay, find the exact length. This is a periodical function. So when sine theta change from 0 to 2 pi, you should get a complete picture. Maybe what you have to be careful is make sure you get a complete curve, but you do not override the gate. Okay, so when theta equals 0, I is 2. Now when theta increases to pi over 2, I is 1. Then when theta equals pi, I is going to be 0. So clearly the picture looks like that. Okay, I can quickly sketch the graph. Then that's the picture. Okay. You just pick up, do the computation in mind and choose the few special values, and you can get the answer. Okay, theta I when 0, I equals 2, when pi over 2, it's 1, when pi it's going to be 0, and 3 pi over 2, 1, 2 pi, you get 2 again. Okay, so you plot those points, you can determine. And on the other hand, you also eyes cannot be negative. So 1 plus cosine theta is always positive. Okay. So you're not going to plot the point on the other side of the line. All right, so that's it. Let's quickly sketch the graph. And so the length is going to be the integral from 0 to 2 pi square root dr d theta square plus You write down this formula first before you do the computation. Okay, before you do the computation, then you plug it. Then you plug the r into this integral. So that would be negative sine theta squared plus 1 plus cosine square theta d theta. Okay, at this moment, we don't see we are able to get rid of the radical. If you cannot get rid of radical, we are not able to evaluate integral, just leave it. But sine square theta, the second part is 1 plus 2 cosine theta plus cosine square theta d theta. Okay, so sine square theta cosine square theta gives you 1, right? Then you get 2 plus 2 cosine theta d theta. So at this moment, you have to recall some formulas in trigonometric geometry to see if we are able to express it as a something square. Okay. So it's 1 plus cosine theta can be something square or not. Okay. Right. Okay. What we know is the formula cosine square 2. Cosine 2 alpha. Cosine 2 alpha is going to be cosine square alpha minus sine square alpha. It's 2 cosine square alpha minus 1 equals 1 minus 2 sine square alpha. Okay. In other words, 1 plus cosine 2 alpha equals 2 cosine square alpha. Okay. Very close, right? So as long as so apply this formula, you will see that this is going to be twice cosine square half of theta. Okay. So you apply that formula to the above problem. It's 2, right? 1 plus cosine theta is 2 cosine square half of theta. Okay, then 2 is taken out. The question is whether you can get rid of radical. At the very beginning, you have to put the absolute value. Okay, it could be negative. Could be negative, right? Yeah, be careful. Yeah, could be negative. So when theta is between 0 and pi, when theta is between 0 and pi, I think it's positive because cosine half of theta is between 0 and half pi. It's cosine half of theta d theta. But when theta is between pi and 2 pi, half of theta, when theta is between pi and 2 pi, half of theta is in the second quadrant. That would be negative. So you have to put a negative sign. Okay. They're not be canceled out because both integral are positive value. Actually, those two are same. Honestly, this is going to be the same. This is going to be same value as this value. Okay. If you draw the picture, it's similar. Why you have to do like that, right? So here's this picture, right? It's 2 pi, and this is a y-axis, right? So cosine, yeah. So without absolute value, whatever you do, without the absolute value, you are going to get a picture like that, I think. Yeah. And when theta equals 2 pi, cosine pi, half of theta is cosine pi. Cosine pi is -1. So but for the absolute value, this is a picture. So this is a pi, right? So they have the same area. Okay, so that's the reason you just need to calculate the one part. So it's 4 times. Okay, that's enough. Okay, then the antiderivative will be sine half of theta and multiplied by 2, because when you differentiate, you will get cosine half of theta and multiply by 1/2. So it's from 0 to pi, okay? And then 8 sine pi over 2 minus sine 0, right? It's going to be 8. So we see that we get same 8. Okay, so this is the answer. Okay, the area yeah, the length is 8. Okay, the length equal to 8. Maybe you want to also find the area later. Okay, so we have a formula for the area of this region. Okay, yeah. So the question is, how do you find the area? Okay, are we able to find the area? Now we don't have any formula we can use. Okay, for the area for region increased by this curve. Yeah, question is how to find the area, okay, increased by this curve, okay. So to solve, maybe we can look at the general case, just a piece of curve like that, okay, and this is going to be theta is between alpha and beta, okay, and this is I equals R theta, okay. So how do we find that area? We have to set up some formulas, okay, that region. Now, this, if you know this formula, then you can, of course, you can apply it to the problem here, okay? Because clear, right? So you have a, right? So I is going to be R theta greater than or equal to 0. Theta is between 0 and 2 pi, right? You can apply it to that problem, okay? So as long as you're able to set up a find a formula for this region, the area of this region, you can apply it to that special case. Okay, this you can apply it to that special case. Okay, so we have to find the formula. How to do that? You have to use a calculus idea. Calculus idea is to partition the region into many small regions. Okay, and then estimate that, and use that to take a Riemann sum and take a limit. Okay, so this is going to be yeah, so you use a partition, arbitrary partition, alpha, okay, theta 0 equals alpha less than theta 1 less than theta 2, all the way to theta n, which is beta, okay? So take an arbitrary partition, then you look at the sector. Look at this sector, okay? Instead of a vertical slice, remember, for the Riemann sum, for the integral area, right? Area of the region under the curve. We'll use a vertical slice and estimate the area, and then of each slide, then you add them together, take a limit, then you get the integral of the function, and that represents the area. But now it's slightly different with the triangle, actually, okay? A sect, right? So look at this. For that small region, okay, what is the area of that small piece? Okay, let's look at this, right? Maybe the curve looks like that if you zoom in. So the angle here, this is going to be delta theta. Okay, that delta theta also depends on the difference of those two, right? And taking the arbitrary value, and you get the radius. Okay, right? Now, so the half of r theta I star squared times delta theta r is the area of that region. Right? I hope you still remember. You learn in high school. This is a sector, just called sector. If you have this is a theta, this is radius, right? The area is going to be half of the radius square and times theta. Theta is in radians. Okay, that's one. When theta equals 2 pi, you get a complete circle. Then it's pi r squared. 2 pi divided by 2 is just pi. Okay, so this is a formula from high school we learned. So for that particular problem, you can approximate, okay, using this sector. So theta is delta theta I, and radius is going to be approximate that, and this theta star is an arbitrary point in that subinterval. All right, so the area, okay, the area is going to be approximated by this Riemann sum. Okay, but if you take the limit, this limit as n as delta theta I all goes to 0, this Riemann sum approaches to the integral, right? Okay, delta theta becomes d theta. All right, so the area formula, we got the area formula right now. Right, simple formula. Great. So this is the formula we derived. Even suppose you don't know the formula, right? We derived the formula. Okay. Someone has to do the first job, right? Okay. So we learn the idea, calculus idea, partition the region or partition, the interval, and then you estimate each small piece, either the area or the length, and add them together and take a limit. Then you get the integral. Okay, and that represents the area or the length of the, in the question. All right. So now let's go back to the problem. Okay, I'm not sure we are able to evaluate this. Okay, so we go back to the problem. I equals 1 plus cosine theta. Theta is between 0 and 2 pi. Okay, find the area of the region. Okay, enclosed by this curve. Yeah, enclosed by this curve. Then, so you get, you write down the formula. Okay, the formula says 2 pi r squared d theta. Now what is r? R is 1 plus cosine theta squared d theta. Okay, we will get, not too bad, it's 1 plus 2 cosine theta plus cosine squared theta d theta. The integral cosine theta from 0 to 2 pi will be 0. So don't worry about it. Cosine squared theta has never been negative. So this gives you 1. Let's write down the cosine. I think cosine squared theta is 1 plus cosine 2 theta divided by 2. Okay. Well, we know that the integral from 0 to 2 pi cosine k theta d theta is always equal to 0 for k equal to integer. That's easy to check. Okay. Because the periodic function, you have a negative part, positive part, they all cancel out. So when you look at this function in the integral, you find out you only needed to evaluate the integral 3 over 2 theta. Okay, so it's going to be 3 pi over 2. Okay, 3 pi over 2. Okay, so the answer is 3 pi over 2. So let's go back to the picture again. This is r equals 1 plus cosine theta. okay? And the length equals 8. The area equals 3 pi over 2. Now 3 pi over 2 is going to be, I'm not sure it's, pi is going to be, you see this is a 2, right? And then look at the unit circle. The unit circle, yeah, sorry, I should draw a better picture. Okay, so the unit circle has area pi. 3 pi over 2 is going to be 1.5 pi, okay? Just 1.5 of the unit circle, the size, okay? Yeah, it's harder to tell, just look at the picture, but based on our computation, that's what we get. So there are not many problems about the surface area using polar curves. We can look at the following problem. Suppose, let's try to derive the formula. So here's a picture, right? Suppose you have a curve here, but maybe it's described by parametric equations. It's described by a graph, right? There are many ways to describe it. It could be y equals f of x. It could be x equals x of t, y equals y over t. It also can be described I equals r over c. Okay, so there are different ways to describe, but if it's described using this, it's also you get special parametric equations for the curve. Okay, now. All right, so we're going to, if with the same curve, I'm going to rotate, rotate about the x-axis. Let's set up an integral for this, okay? For the area of the surface. Okay, so this surface, we assume that obtained by rotating the curve r equals r theta. Okay, theta is between alpha and beta about the x-axis, for example. Okay, how do you do that? Well, we have a basic formula. It's 2 pi r ds. That's it. This is the only formula you need. So on the map, on the picture, you have to mark what is x and y, right? And then you have to make sure there's a radius. So express the radius in terms of theta. That's it. Okay. So you see that now this side is not that r, okay? So you can it's going to be 2 pi for this particular picture, it's 2 pi y and ds, right? Yeah, 2 pi y and ds. Now, if you want to use the theta, then it will be theta from alpha to beta, 2 pi. How do you express y? Y is going to be r theta sine theta. Okay. If you look at the picture, you can see that this is r theta, that's a theta, so sine of that gives the radius. Okay, and here will be, we already calculated that d prime theta square r plus correct d theta. So that just, you know, yeah, it's just the small difference here, right? So this is the ds. Okay, so let's look at the picture again. Now that's my favorite picture. It's a hut, right? Okay, yeah. So the equation is r equals 1 plus cosine theta. So you should design a Valentine's card. Just put this equation on the first page. So you don't need to draw the picture, okay? Anyone who understand that, understand what you mean. What do you mean, okay? So we already find out the area, right? We find out the parameter, right? Now let's notate it about the x-axis, okay? So you get, right? You get some solid. It's around the solid, okay? So how do we find the surface area of this? It's, yeah, imagine how does it look like? If you, I think it looks like if put on the top, it looks like that, right? It's hard to draw it, but inside, yeah, it looks like that, okay? Yeah, I don't know how to draw it. So anyway, this is a, yeah, let's set up an integral. Maybe we can evaluate. So based on the above formula, right? So the surface area is going to be from 0. Now be careful. You just need a half of that, okay? Because the bottom part, is top part will give you the same. So just need a half of that from 0 to pi. That piece of curve you generate, yeah, that one, okay? That one, if you rotate that curve around the axis, you get the surface, complete surface. That's why it's from 0 to pi, not from 0 to 2 pi. Okay, and the 2 pi and r, right? R is 1 plus cosine theta, and then theta, right? And what's inside? Remember the inside one, it's going to be r squared plus so it's going to be, you know, it's going to be 1, yeah, so 2 plus, yeah, 2 plus 2 cosine theta, okay? So that is going to be, yeah, we already did a computation here. One plus cosine theta, sine theta, and cosine half of theta. I should say that we are able to evaluate this integral, just a little bit complicated. Okay, this is we can do that. Okay, because yeah, it just takes time. You can evaluate the integral sine theta times cosine half of theta, right? You can also why we can evaluate this integral. Let's do it one by one, right? So if you multiply this out, you get sine theta cosine half theta, and this one sine theta cosine theta, right? You can simply write the sine 2 theta. So it's going to be the product of two functions. Then you can you can use the formula. Do you still remember the formula? How to decompose it? Okay, let's recall the formula. Okay, we know that sine alpha plus beta is going to be sine alpha cosine beta plus cosine alpha sine beta, right? But if we change the sign for the beta, okay, so in order to get sine alpha cosine beta, get them together. Add it together, you get half of sine alpha plus beta plus sine alpha minus beta, okay? If alpha is first. So using this formula, okay, using those formula, you can integrate, okay? Here alpha is theta, beta is half of theta. So I'm going to get sine, right? Theta half of, yeah. Alpha is theta, beta is half theta. Add them together, I get 3 theta over 2. Now, if I do subtraction, just sine half of theta, okay? It's not too bad. So then half, 1/2 is quarter, okay? And here, add them together, that is going to be 5 theta sine 5 theta divided by 2, and plus subtraction the sine 3 theta over 2, okay? Then how many terms you are going to have, okay? Yeah. I'm going to take the pi out, okay? So take a 4 out. I get 2 sine 3 theta at 1, so I get 2 sine half of theta. I get 3 sine 3 theta divided by 2, and then I only get, then I get sine 5 theta over 2. So you can evaluate the integral. Okay, why there's 3 here? If you take the 4 1/4 out, then you get double of sine 3 theta over 2, then another one, right? Yeah. Okay, so that's the, okay, then you find the antiderivative. Okay, let's do this. It's going to be negative 4 cosine half of theta. Okay, negative. So this will be, let's look at, right, when you differentiate, yeah, you have to put 2 here, so then I get 3, cancel out. And then negative 2 over 5 cosine, right? Then you plug the number into, you should get a positive number, right? Yeah, we have a couple minutes. I'm going to finish this. Okay. So cosine half pi. Okay. Let's see. Cosine half pi is going to be 0, right? Cosine 3 pi over 2 is 0. Okay, so actually they are all 0. Cosine 5 pi over 2 is also 0. Cosine not 0 is when pi and 0. Okay, so minus pi cosine 0 is 1. They are also 1, right? So it's not that complicated, because they all equal to 1, because cosine 0 is 1. So negative negative becomes positive, and what I should get is, I guess, 6 plus 2 over 5, and 32 over 5. So 32 pi over 5. Okay. So the area of that is going to be 32 over pi. 32 pi over 5, sorry. Yeah. So we can find the surface area of that region. It's a good example, yeah, that surface. What you have to be careful is about the domain, you know, from 0 to pi. Otherwise, you double count. Okay. So problem on the test on this will be more like this type of function. Let's quickly go over different type of functions. So what if I equals 1 plus cosine theta, we know that it's a hot, okay? But if I equals 2 times plus cosine theta, it's not going to be hot, okay? When it's going to be 3, when x pi is pi, when theta is pi, that'll be negative. It's still positive number, so it's going to be like that. Okay, this is a 1, radius equals 1 here, radius equals 3, and this is I equals 2, and this side is going to be 0. Right? But if I equals 1 plus 2 cosine theta, then that's a problem here, right? When theta equals 0, it gets 3. Right? When theta equals 3. But then you rotate. It looks like that. Okay. Not exactly. This picture is wrong. Okay. We have to make sure when the I is 0. Okay. When the I equals 0. Okay. When I equals 0, it's 1 plus 2 cosine theta is 0, right? Cosine theta equals negative half of 2. So that means theta equals pi plus minus pi over 3. Okay. So that means only when along this, okay, the I is going to be 0. So my graph should be looks like that. Okay, tangent to that point. Okay, so that's good. You have to pass the y-axis. So those are the 3 typical graphs, and you can tell that there's a small change here, right? The middle one, 2 is larger than 1, right? So you just make sure whether the R can be 0 or negative. Okay? If R is negative in some direction, you have to plot the point like in this direction. I is negative, we have to go the other side to plot the point. Yeah. If the angle here, for this angle, I is negative. When I is negative, you just plot the point on the opposite direction. Okay, that's the reason when you're trying to draw the graph, and you draw the graph curve on the back side, it's the front side. Okay, when you rotate this line, about the origin, okay, then the very beginning I is positive. Imagine gradually I is decreasing at the angle pi minus pi over 3, I becomes 0. Okay, so you get to the origin. Then after past this angle, I is negative, so you have to draw plot the point on the back side. Okay, right. Then that's why you have another closed curve over there. Okay. Now, if I ask you to find the region between those two pieces, two curves, then you be careful about. It's not easy to do that. You have to figure out. Yeah, maybe take the difference of those two regions. Okay. So this is that's all about today's lesson. Okay. My favorite example is still 1 plus cosine theta, and we did 3 different type of problems. We find the arc length. We find the area enclosed by this curve, In order to find that, we derive the formula for the area, right? And using Kaker's idea, okay? Then we also locate this curve, half of the curve, about the x-axis, and then you get a surface. And we are curious about surface. We eventually can evaluate the area of the surface, okay? If we're careful enough, okay? So if this is a problem on the test, I think the most important part is the setup, okay? This is the most important part. So I promise you, if you write down that, you get already 80% of the credits, okay, on the test. Okay, then you, if you have a time, you come back to the evaluation. So you have to manage your time very well. Don't just focus on one problem. Spend too much time for that particular problem. You have to look at how much time do I have left and how many problems behind that. Okay, maybe some problems very easy. You can easily get 10 points instead of get behind the schedule. Then you're in hurry and you cannot focus, cannot solve the problem. Okay, so today I give you more time to take the quiz.